Hi guys, this is Mr. Hart. In class we didn't quite finish this proof off, so I wanted to go through it on the Livescribe so they could see what we're trying to do. And again, we kind of take this equation right here at the top for granted a lot of times because it just kind of is given and we assume it's true. But the fact that we're allowed to take the average velocity and times it by the time and get the total displacement is really quite phenomenal, and it's a special property of these quadratic functions. And so what we want to do, and as we talked about in class, is we want to be able to show that the average velocity between 2 points on a quadratic is also the average of the two instantaneous velocities for those 2 points. Okay, and we can also show that the instantaneous velocity halfway through the graph is also the average of the two instantaneous velocities. Now, to fully complete the proof, we'll have to do some integration later on in the year, but you can kind of see already at the top of this equation the average velocity, or I should say the average of the velocities, is a key component of this. And so we have to be able to show these two parts. So basically we're given this equation here that x of t equals x naught plus v naught t plus 1/2 at squared. And we're trying to show these two things. Okay. So this one right here shows that the average velocity, just given the simple rise over run equation, equals the averages of the average of the two instantaneous velocities, and also that the in this equation right here that the average position, or sorry, I should say, well, I guess it is the average position halfway through the quadratic has the velocity that is the average of the two velocities. Okay, so we're going to show both these things right now, and then when we get to integration, we'll probably show off the rest of this proof, but it's really quite simple. We just integrate once and we're there. But let's prove each one of these individually. Let's start with the left side first. Okay, so let's say, by the way, this is a common mathematics notation to have a given, show, and proof part. But let's say we're trying to prove this, so let's just start on the left side. So we have x of t final minus x naught over t final minus 0. That's a simple rise over run equation. Now, that is going to be equal to plugging this t final into the equation above, this x of t that we were given, which is our general quadratic for position. So we'll get x naught stays the same, plus v naught times t final, okay, plus 1/2 a t final squared. Okay. Now, I don't really need those parentheses, but I'm going to write them down just to show that we're substituting that in. Then we're going to minus that from, I should say x of 0, but it's also x naught, right? If we plug in 0, then all the t's go away, and we're just left with x naught in the equation up here. Okay. So then that's all over t final minus 0, which is just the same as t final. Okay. So then we can simplify. The x naughts on the left and the right of that thing are going to cancel out, so we're just left with v naught t final plus 1/2 a t final squared all over t final. Now one of the t finals is going to cancel out, and we're left with v naught plus 1/2 a t final. Okay. So there we go. That's what it simplifies down to. Now we can do a little bit of simplification. Since we know that a equals v over t, right? We can also say that a times t equals v. Okay? Well, in this case, if we're taking a times t final, then that's going to be our velocity final minus our initial velocity. Okay, so if we want to be really particular, this is change in velocity, right? And that's going to give us the following. Okay, so if that's the case, this is going to imply that this thing above, this equation above, goes to v naught plus 1/2 times the change in velocity, or v final minus v initial. Okay? So moving on to the next page, I'll just rewrite that really quick so that we have it. v final minus v initial. And so last step is just to distribute that out. So we get 1/2 v final minus 1/2 v naught. Okay. 1 v naught minus 1/2 v naught is just 1/2. So we get 1/2 v naught plus 1/2 v final, which gives us what we want, which is v naught plus v final over 2, the average of the instantaneous velocities. Okay. And then in math, you'll see them often write this little square to show that you're done with the proof. Okay, so now next step is that we want to show the halfway instantaneous velocity. So we just finished our first proof, so we're going to do the second part. And so for this, first of all, let's just find x prime with respect to t. Okay, x prime with respect to t is just going to get rid of that x naught. It's going to leave us with v naught plus a t, right? I'll write it up here in case you can't see it. But x of t was x naught plus v naught t plus 1/2 at squared. Okay, x naught goes away, v naught t just becomes v naught, and then 1/2 at squared, the 2 comes down, and it just becomes at. Okay, so if we're trying to find x prime of t final over 2, we can just substitute, which becomes really easy, because it's just 1/2 a t final over 2. Now we have the exact same thing as before. Okay, I probably don't even have to write these steps, but you'll notice at final over 2 is the exact same as 1/2 at final, which we just showed was, I can go through the steps again, but it's v naught plus 1/2 v final minus v naught. Okay, and just like we did before, we end up with v naught plus v final over 2. Okay, and there we go. So we have our two proofs there. So we just showed that the average velocity is the average of the two instantaneous velocities, and the instantaneous velocity halfway for the quadratic is also the average of the velocities. Okay. So basically, again, we don't have integration per se. Some of you may have already learned this, but you can just imagine if we have velocity of time, okay, and it's equal to, we could say v naught plus v final over 2 for any t final over 2. If we basically just integrate that and go back up a step, okay, we treat that as one value, and so we get x of time just equals that thing we had times the time, which gives us that equation we had before. Okay. And so I'm doing a little bit of hand waving at the end, but once we've established these results, okay, then we can show that equation that we had before. But this is cool. I think this is cool about quadratics, that they have these two properties. Okay? There you go. Thank you for listening and watching.